All right, so now we get to talk about multiplying and dividing with complex numbers. So as you can imagine, if we have two complex numbers and we want to multiply them together, it's kind of like having two binomials. So we can use our FOIL process to multiply those together. So when you do this, you multiply the 5 times 2 to get 10, 5 times 6i to get 30i, negative 3i times 2 is going to give us a negative 6i, and then here, negative 3i times a positive 6i gives us a negative 18i squared. Now the thing is, I mean, you can combine these pretty easily, but the thing is, right here, I squared, you got to remember that that's equal to negative 1. So negative 1 times a negative 18 gives us a positive 18 here. So if you're not careful about that, that's a very easy mistake to make. So now we can add the 10 and the 18 to get the 28 plus the 24i. And no, you don't have to factor out anything. We want it to be a complex number just like that. Okay, so we've talked about conjugates before. There is such a thing as a complex conjugate, so that's when you're dealing with these complex numbers. And of course, they come in pairs, and they're almost exactly identical to each other, only one you're adding the bi, and the other one you're subtracting the bi. And what's interesting is that there's a complex conjugate theorem that says that when you multiply complex conjugates together, the result is the sum of squares. So if you look at this, a plus bi multiplied to a minus bi, well, you get the a times a, which is a squared. The a times a negative bi and the a times positive bi, those drop out. Bi times a negative bi, well, that's b squared, and then the minus, so a negative b squared, but then the I times I, that's I squared, that's going to be a negative 1 as well, so that negative b squared turns into a positive b squared. All right, so this is really useful. So remember this. It makes the process of doing some of these problems pretty quick. So if we were going to factor x squared plus 3, typically we would say cannot be factored, and we would be done. But if we get to use our complex numbers, we actually can factor this. So first of all, we can look at this and think of it as the sum of squares. Even though this isn't a perfect square, we can take the square root of it and we just get square root 3. So we can actually write this answer as x plus I root 3 times x minus I root 3 using our complex conjugate theorem. So we're going from something like this to factored form. Okay, so keep that in mind. Another thing that we use our complex conjugates for is to rationalize the denominator. Remember, we don't like I to be in the denominator, just like we don't like radicals to be in the denominator. But if we ever have a complex number, we can't just multiply the top and bottom by the imaginary part of 7i, because when you distribute, you would get 6 times 7i, and you still have I down there. So to get rid of it, what we're going to do is multiply the top and bottom by the complex conjugate. So in the numerator, we're going to FOIL this out, and in the denominator, we're going to use our complex conjugate theorem. So this is what it looks like when you've FOILed it all out. Okay, remember that I squared is going to turn into a negative 1, so this is actually 12 minus 35 to give us negative 23. And then these combine to give you a negative 44i. On the bottom, 6 times 6, or 6 squared, you get the 36. The middle terms drop out. And remember, this is going to turn into a positive, because it's a sum of squares. So you square the 7, and you get the 49. So you're going to add those together to get 85. And that's your answer. That's the same number, but with the denominator rationalized. Okay? Last one, if you want to factor x to the 4th minus y to the 4th, and you're allowed to factor over the set of complex numbers. Let's just try this one more time. First of all, this is the difference of squares. So we have x squared minus y squared and x squared plus y squared. And this right here is the difference of squares. So we get x minus y times x plus y. And typically, we've had this problem before, we would have stopped at this point and said, this is as factored as it possibly can get. But now, because we get to use the complex numbers, This being the sum of squares, we can actually take it one step further and write these as a pair of complex conjugates. All right, there you have it. Multiplying and dividing complex numbers. Wasn't that fun? Bye!